in our neighborhood, University of Illinois at Urbana-Champaign. His research interests are in network and distributed system security, and he's currently working on projects in secure messaging, dynamic coalitions, web services, and wireless sensor networks. Here's Dr. Kuru.
Thank you, Lingui. As Lingui said, I'm Himanshu Khurana from the National Center for Supercomputing Applications. I'll be talking today about an approach we are trying to propose for minimizing trust liabilities in secure messaging infrastructures. Please feel free to interrupt me anytime with clarification questions or comments. That's no problem at all. So many large-scale collaborative applications need a messaging infrastructure that allows the collaborating entities to talk to each other or exchange messages without concern for message transmission and delivery. For example, groupware applications today typically assume the presence of an email infrastructure for group communication. Conferencing, such as video conferencing or audio conferencing, assume the presence of multicast group communication infrastructures. Tickers, such as stock tickers, news tickers, etc., assume the presence of a PubSub infrastructure and take advantage of it. However, for widespread deployment and use of these such applications, you need a secure messaging infrastructure. And by secure, we mean an infrastructure that provides support for integrity, authentication, confidentiality, and availability. Integrity and authentication is typically provided today by the use of digital signatures and together with certificate authorities and public infrastructure. So they work pretty good, but they impose large certificate distribution revocation problems. Confidentiality is hard to provide in messaging infrastructures, and wherever it is provided today is done by the use of trusted servers that do key management on behalf of the users. Consequently, the servers bear significant trust liabilities of maintaining the confidentialities of those messages and keys. For example, a group controller in a group communication system today can store all the long-term session keys, long-term as well as the session keys. Availability problems can be solved via replication, but with the caveat that if you replicate any server with keys, you can reduce the security of the system. The focus of our work is specifically on confidentiality. That is, how can we make messaging infrastructure support confidentiality but minimize the trust liability that is borne by the servers providing this security support? So why is this an important problem? So it's an important problem because servers are now being attacked on an increasing basis. Electronic crime is on the rise. For example, in the summer of 2004, there was a large-scale attack on the supercomputing infrastructure of this country. Many systems at NCSA were compromised, at San Diego, and etc. The attackers there compromised remote users, used these user accounts to go to the servers, and did privilege escalation attacks to get root access on servers. And they did a combination of denial of service, some integrity modification, or they were planning maybe just using the systems to launch denial of service attacks elsewhere because they didn't have access to this great network infrastructure. And I'll go into this a little bit more detail, but they specifically tried to violate the confidentiality of email in the system, specifically the email of the security administrators. So we want to provide resources that minimize this trust liability so that even if the servers are compromised, you do not lose confidentiality of all data and communications in the system. This is not an easy problem to solve. If we say that the servers should not have the keys, that directly means that the server should not be able to access the messages that traverse the messaging infrastructure. However, it is these servers that must process these messages in order for delivery. For example, in publish-subscribe systems, the broker network does the matching and routing on the messages in order to deliver it to subscribers that have interest in those events. As I mentioned earlier, in group communication systems, the servers must process the key management messages in order to update the session keys whenever a member joins or leaves the group. Furthermore, the solution must scale to support a large number of users. This specifically means that you cannot have any key establishment between the end entities, which is clearly an order n squared problem and leads to higher overhead. So our approach to address these challenges is to explore novel encryption techniques and then use these techniques to design messaging infrastructure. To study this problem, we have chosen three specific infrastructures, namely group communication, publish, subscribe, and email. At the end of the talk, we'll see what characteristics of these systems are related and what other systems could be there where this could be applied. The encryption techniques that we look at is namely proxy encryption techniques. This is an idea that came about in the late 90s, which allows a transformation agent to convert ciphertext from a ciphertext that is a message encrypted with one key into ciphertext for another key that is a message encrypted with another key without revealing the plain text or the secret keys to the transforming agent. So let's look at an example construction in El-Gamal. So in El-Gamal, let's say the keys for users A and B is as follow. SKA is user A's decryption key, while PKA is his encryption key. Similarly for user B. Let's say we have transformation agent T, to which we give a proxy key called pi, which is the difference of the decryption keys between users A and B. Now you encrypt the message for user M, user Alice A, as follows. This is the standard El-Gamal encryption of the message. And you want the transform agent to transform the message such that the outgoing message is encrypted for user Bob. What T would do is to take the message and simply encrypt it with a function of the proxy key. With simple mathematics, the private keys here cancel out and you get a message that's encrypted with user Bob's public key. Now here, the transformation agent only has access to the proxy key, not to any secret keys. So consequently, the trust liability in the transform agent is minimized because it no longer has the decryption keys, but can still enable the transformation. The applications that have been looked at earlier in this context are key escrow. For example, escrow with description escrow for the FBI or something, smart card key management, and file sharing, where one user wishes to delegate to a transformation agent the capability to assign decryption rights for files. To our knowledge, we're the first to look at extending these schemes and then analyze them in the context of large-scale collaborative applications. So in the next few slides, I'll take one messaging infrastructure at a time and show how these schemes need to be used and how this minimization is realized. So first is email list services. This is something we're all familiar with, as they typically clog a large percentage of our inbox on a daily basis. An email list service comprises a list moderator, which is a process or an entity that creates lists and subscribes users. Then there's a list server that creates lists, forwards emails to all valid list subscribers, and optionally archives the emails as well. And then there are users or subscribers that subscribe to lists with the help of the list moderator and send and receive emails with the help of the list server. The reason why these mailing lists or email list services are so popular is because the list server bears all the overhead of list management and forwarding the emails. The user has to do little or no work. They are increasingly popular for exchange of both public and private content. Whenever there's private content involved, security becomes an important concern. For example, there are currently over 300,000 lists registered on listserv, which is a common list server system, while only 20% of the sum public content, meaning the large amount of content is private. However, that private content is not actually supported by any security techniques. They just say that you do not have access to it, but there is no cryptographic support for this privacy. So there is need to develop solutions that provide security in this environment. There has been a lot of work done for two-party email exchange security, but definitely not enough for mailing lists. To that end, we have developed a solution called SELS, Secure Email List Service, that provides solutions for confidentiality, integrity, and authentication. So why do we need these security properties, and what do they mean in this context? Confidentiality means that only authorized users, that is, the list subscriber, should be able to read the emails. In particular, this means that the list server is excluded because it's actually not a valid list subscriber. Integrity and authentication have more standard meanings. Integrity means the receivers must be assured that the email has not been modified in transit, and authentication would allow receivers to verify the sender's identity. Our focus here is more on confidentiality, so I will not go into details of integrity and authentication, except to say that they are more or less done by using standard PKI techniques. So now a little more deeper, a few more examples of where do we need this confidentiality. is there actually sensitive information out there that needs this technology and this support? So I started out by saying that this is important for maintaining the privacy of sensitive information. For example, you have security lists concerning infrastructure protection. So we have some system administrators at NCSA and elsewhere that often discuss vulnerabilities and system characteristics, and they wish to keep this information away from the hackers. Today, they actually use an offline key distribution mechanism where they exchange emails on the phone. So they exchange passwords on the phone and then use that to encrypt the emails. So we need to provide a better solution for them. Another example could be executives discussing corporate strategies, where the corporate strategies will concern sensitive information. In healthcare research and development, you can imagine a group of researchers discussing healthcare issues, and they will need to encrypt any information to enforce HIPAA laws. That is, if they want to use email to do the research, but email is a very interesting, a very commonly used infrastructure, and it would be great if it could be used for a lot more purposes than it is done today. When you add integrity and authentication to the mix, secure email lists become important in all groupware applications, such as document annotation and storage, distributed software development, and mobile teamwork. So let's see how we do security for two-party email exchange today using something like PGP. Here, Alice has Bob's encryption key in her keyring, and Bob has Alice's signature verification key. Alice composes the message plaintext M, signs the hash of the message with a signature key using something like RSA or DSA, then chooses a random symmetric encryption key K and encrypts both the message and the signature using algorithms such as AES or TripleDES. She would then encrypt the symmetric key K with Bob's public key using something like RSA or Elgamal, base64 encode the whole message and send it off to Bob. Bob would use his decryption key to decrypt the message, specifically decrypt the symmetric key K, then further decrypt this entire part of the message and verify the signature. Other approaches such as PEM and SMIME are actually aligned, have very similar approaches to solving the problem. They work, but they're not used as prominently because of certificate distribution and revocation issues. An approach proposed recently that minimizes the distribution problems is identity-based encryption, where Alice would be able to derive a public encryption key for Bob using his email address alone. But if you try to use any of these solutions and extend it to a list scenario, you face a couple of challenges. The way to do it while ensuring minimum overhead for the users would be for the sender to encrypt the email with the list server's public key, for the list server to decrypt it and then re-encrypt it for every valid list subscriber. We have two problems. First, the confidentiality requirement is not met because the list server now can read the email contents. And secondly, an adversary can now compromise the list server to get access to all the emails that the list server maintains. That is, there's a high trust liability. So what are some approaches to solve this problem? One, as I said, like it's done today, you could just exchange a symmetric key out of band. But it's difficult to provide secure key distribution. You could just use a PGP web of trust, where the senders maintain all the receivers' PGP public keys for encryption. Clearly, there is a high key management overhead for each user. Or you could use cryptographic hardware, where the emails will be decrypted and re-encrypted in a crypto lockbox, such that it's difficult for the adversary to compromise that. Unfortunately, these lockboxes are expensive, costing anywhere from $3,000 to $10,000, and they also have been broken in the past. Our approach to this problem is to use software-based re-encryption techniques at the list server to transform encrypted email between the senders and receivers without the list server requiring access to email plaintext. So here's an overview of our protocol. So we have our entities, the list moderator, the list server, and a bunch of users that wish to subscribe to the email. When the group is created, the list moderator establishes a key called KLM. This is our Elgamal keys in a publicly known parameters. And the list server establishes a corresponding list key. They both implicitly agree that the sum of these keys is the list key, though neither knows its value. When a user wishes to subscribe to the email, it sends a join request to the list moderator. The list moderator replies with some key material that allows the user to establish its decryption and encryption key pair. it then completes the subscription process by sending a message and some key material to the list server, who establishes a corresponding list key for the user. And the idea is that the sum of the user's private key and the corresponding private key is also KLK, the list key. Once the users have subscribed to the list, you can send the email. The users would simply send signed and encrypted email to the list server. The list server would do the transformation and then forward the emails to all list subscribers who can decrypt and verify the signatures. An assumption here is that the list moderator is an independent entity not controlled by the list server. And the reason for that is if you compromise both KLM and KLS, you get KLK, and that can allow the adversary to violate the confidentiality of the solution, of the system. Okay? So how does it look like, putting it back in the format in which we saw how PGP works? Here Alice wants to send a message to the list, so she sends it to the list server. This part is exactly identical to what's happened earlier. Now instead of encrypting the message with the receiver's public key, she encrypts with her own public key and sends it to the list server. For a given list subscriber Bob, the list server would simply transform this part of the message and send it out to Bob. The transformation process mentioned here down below is very similar to what we saw as an example Elgamal transformation. That is, the list server simply encrypts the message with Alice's proxy key and decrypts it with Bob's proxy key to give a result such that the outgoing message is encrypted with Bob's public key. So the overhead is about the same as a decryption and re-encryption, but you minimize the security liability in the list server. We have recently formally verified the security of the scheme using ProVerif, which is Bruno Blanchet's formal verification protocol. It's a fully automated protocol verification tool. And now we're doing a prototype design and development. So for the client side, we're designing a web-based subscribe function that's integrated with the GnuPG tools to generate standard PGP keys. So once we do this, any email client that employs a PGP plugin can use these tools. Now this is very important because we cannot say, if you want to use our solution, use a new email client. People are not going to do that. So we have to make the effort to integrate it with PGP. That's the most commonly used security tool out there. And then, of course, we'll work on integrating with SMIME as well. And I don't think that should be a big problem. Now, on the server side, we're developing some plugins for MajorDomo and Mailman, which are the two most commonly used list server software. So that was what we have done for the email list infrastructure. And the idea is to use proxy encryption to minimize the trust liability in the list server. So now I'll move on to the second messaging infrastructure that we used, namely publish subscribe. So this is a relatively new but very powerful messaging paradigm. The idea is that there is a publish subscribe infrastructure comprising a bunch of brokers and border brokers. There are publishers that register with border brokers and advertise and publish events, for example, stock quotes. The broker network does the matching and routing of these events and then delivers them to subscribers who have registered interest in those events with the border brokers. So the publishers and subscribers do not interact directly. Instead, they use this messaging infrastructure, the PubSub infrastructure, to do the event routing. This messaging paradigm has applications in many areas, from software updates to location-based services and so on. As I mentioned, one commonly used example in this context is stock quotes, where the publishers just publish the stock quotes and the infrastructure figures out which are the subscribers that will be interested in these events and routes it to those events. There are three types of PubSub infrastructures. There are topic-based, where the matching and routing is done on the subject or the topic of the event. Then there are type-based, where all the event types are organized in a hierarchy, and you can use some hierarchical rules to do the matching and routing. And there are content-based, where the matching and routing is done on the entire contents of the messages. Clearly, content-based is the most general, and that has been the focus of our work. So what is the confidentiality problem here that we worked on? So the idea is that you want to deliver information that has been published by the publishers only to authorized subscribers and to nobody else. And you want to do it in a way that where the publisher and subscriber do not trust the broker network. By that I mean, if you look at it, suppose as a publisher I trust a broker network, then I don't need to bother with extensive cryptography. I can simply give the message to the broker network and the broker network will deliver to the subscribers. But that's not a very realistic assumption, because in an internet scale publish subscribe infrastructure, the broker network will comprise peer systems, and it's very difficult to assume that the entire network of peer systems is secure and can be trusted. Second, and a closely related problem, is usage-based accounting, which also motivates the need for confidentiality. Now, the publisher publishes stock quotes but wants to charge subscribers for the quotes that they have actually received. How do they do that? It's not an easy problem to solve. So we solve these two problems in a strong adversarial model setting using proxy encryption. That is, the publisher and subscribers don't trust the broker network. That implies that an adversary can read all the network traffic that traverses the PubSub infrastructure. The adversary will attempt to violate the confidentiality of the messages by reading them, and possibly modifying the integrity and authentication by trying to insert fake events or modify existing events in the network. Another strong point of our solution is that no modifications are needed to existing matching and routing algorithms. So here the problem is kind of easy to see. If you don't trust the publish-subscribe network, you cannot let brokers have access to the events. But it is precisely on the contents of these events that the brokers do matching and routing. So how do you solve the problem? One approach is to perform computations on encrypted data. So you encrypt the data from the publishers, and then the brokers would do all their matching and routing on the encrypted data using special functions. Now, these functions have been designed in theory, but they're very difficult to implement in practice. Furthermore, they also require modifications to existing matching and routing techniques. So our approach to this problem is based on the observation that only selected parts of an event's content need to be confidential, and matching and routing can be done without these sensitive parts. So what do? We encode the events in XML documents, and we selectively encrypt sensitive parts of the events. To do so, we use Bertino and Ferrari's XML document dissemination techniques. The next problem is now to distribute these keys to authorized subscribers. For that, we use Jacobson's proxy encryption techniques. So let's see how that's done. So first I said, so let's give me an example of what we mean that you can actually encrypt only sensitive parts of contents. So the first example here is our stock quote dissemination service, and it's a stock quote price, and the publisher decides that this can be commonly agreed upon, that the only sensitive part is the current price of the stock quote. So you encrypt the stock price with a symmetry key K, and you leave the remaining part of the event contents in the open, and you allow matching and routings on other fields such as the volume, the name of the stock, the opening price, etc. The example below is a game score ticker, where in a similar way you can encrypt just the current score and leave the other parts unencrypted. Now, you have the sensitive parts encrypted with a symmetry key K. The challenge is, how do you get this key to authorized subscribers? If the publisher and subscribers could talk to each other directly, then the publishers would simply encrypt it with the subscriber's public key. But that goes against the philosophy of publish-subscribe, where you don't want the publisher and subscribers talking to each other directly. So the way we solve this problem is using a proxy service. So the publishers will encrypt the symmetry key K with the public key of the proxy service. Public key of the proxy service is PKPS, for which the decryption key is stored in a threshold manner in a set of servers at the proxy service. So here's how this happens, how this works. So the publishers publish the event where the selective parts of the event have been encrypted. The border brokers do the matching and routing on the clear text contents. The events reach a border broker that has a subscriber with interests in those events. The border broker then requests a transformation of the event with the subscriber's public key to the PSAS, the proxy service. The request is picked up by a set of coordinators that verify the request and sign the specific transformation task. That is, the transformation of the symmetry key K from the proxy's public key into the receiver's public key. And then we run Jacobson's proxy encryption technique, which is a threshold decryption and re-encryption algorithm, on these servers to generate the result. Here's another view of the same process. What that does is essentially the server simply decrypt the key with their decryption key and re-encrypt it with the subscriber's public key. But this happens over a set of servers so that the plain text is never recreated in any single place. Furthermore, at the end of the transformation, the PSAS also generates a verifiable certificate of the transformation. By verifiable, it means that it's a publicly verifiable certificate that would allow any third party to verify that this key was actually transformed between this key and between this public key and the other public key. Yes?
But in a public subscriber, you have a publisher, subscriber, and the broker.
Yes.
Where does the PSAS fall in this?
Yes.
It's a new entity, right?
It's a new entity. So, so the first thing that happens is if you introduce a new entity, your question comes, it's centralized, potentially. That's not a good thing. And second is also performance issues. So yes, we are introducing a new entity, and I'll talk about that in the next slide. So this verifiable certificate is what allows the publishers to provide usage-based accounting, because now it is a proof that you can charge the publishers, you can charge the subscriber based on what they have used. So now, as was just pointed out, if you have a single PSAS service for an internet scale publish subscribe system, you raise issues of centralization as well as performance. So we've done some scalability studies on this system, and we work backwards. So we need the transformation every time you deliver an event to a subscriber. So working backwards, we looked at what are per subscriber event delivery rates that you typically need. So we said that if you want a frequent delivery of events, every subscriber will receive an event every minute. More reasonable is something like an event every 20 minutes. And then we looked at the architecture, and it turns out that, like most public key systems, the performance bottleneck is the exponentiation. So we looked at performance exponentiation measurements on common desktop and server systems, and for a reasonable price desktop, we get a range over here. So our scheme, depending on the frequency with which you want to deliver events, delivers somewhere between 20,000 and 50,000 subscribers per PSAS using current technologies, which is reasonable for many applications, but maybe not enough. Then the issue comes of centralization, where you can actually replicate the PSAS and have solve the availability problem that way. And furthermore, by replicating, you also increase the scalability of the system. And the scalability increases approximately linearly. So if you have 3 PSASs, you triple the overall service rate that you can provide. So the cost is high, and we need to do more work to see if there are ways in which we can reduce the cost or provide other techniques. But this is a solution to this problem, which has been a hard problem to solve and was proposed about 2 years ago. And to our knowledge, no other solution has yet been proposed. Now, moving to the third messaging infrastructure, namely group communication. So secure group communications is needed to support many military and commercial applications. For example, conferencing, command and control systems, and interactive distance learning. Here, the need for confidentiality has been clearly stated by many of these such groups. And what you need is a group key management solution. So the way they solve the confidentiality problem is they give all the group members access to a session key that is used for encrypting bulk data. Whenever a user joins or leaves the group, you need to update this session key to ensure security. And if the group is large, you have your key management problem, because now you must update this session key in an efficient and scalable manner. So a lot of schemes have been proposed to solve this problem, and we broadly classify them into 2 categories. First is logical key hierarchies that use a trusted group controller. Here the group controller maintains a tree of all the long-term symmetric keys and efficiently update the session key on change. Basically, it pushes it out. The drawback is that the group controller is completely trusted. So if an adversary compromises the group controller, it gets access to all the long-term keys as well as session key of all the groups that the group controller supports. On the other kind of schemes are more decentralized or contributor key agreement schemes, which are perhaps more elegant in nature and do not involve a group controller. and they update the session keys amongst the users using distributed protocols. Unfortunately, they do not scale as well and also impose a slightly higher overhead on the individual group members. So what we have done is use the proxy encryption idea to try to get the best of both worlds to some extent. Our scheme is called Task, which is a tree-based group key management scheme with asymmetric split keys. The scheme is as efficient and as scalable as LKH, essentially order log n. Furthermore, we have a partially trusted group controller. That is, the group controller does not store encryption keys. Instead, it only stores proxy keys to do the transformation. So even if the group controller is compromised, the confidentiality of the message is not lost. Therefore, the group controller is no longer a single point of security failure. Furthermore, recovery is much simpler because you have not lost any long-term security secrets. The assumption for our protocol is that all messages are signed, and this is a common assumption by most group key management protocol. Another problem is that the group controller and a member are not simultaneously compromised, and I'll talk about this assumption a little later. To get an idea of how our keys work, here are the key trees for both LKH as well as Task. So on the left is LKH. As we can see, these are all symmetric keys. On the top half are the keys that are stored in the group controller, and bottom half are the keys that are stored by the member. Each member has a set of keys, specifically order log n, from its position in the leaf node all the way to the root. The group controller uses the long-term keys as well as intermediate node keys to update the session key for each member. And the session key is nothing but the root key here. For our scheme Task, these are all asymmetric keys, in particular Elgamal keys. And the keys are not common to members and group controllers, but they do have a relationship. For a common index, the private keys at the member and the corresponding private keys of the proxy keys at the group controller add up to the same value called GKEK, the group key encrypting key. The session key is a hash of the root private key stored by the members. Since the group controller does not store the session key or the long-term member keys, its trust liability is minimized. But the fact that it has these proxy keys allows it to do the transformation in an efficient manner. So let's see how the proxy stuff works for member leave event. So we have a group of 9 members, and member 9 decides to leave. It sends a message to the group controller, or it lost network connectivity and it needs to be kicked out. Now we have to update the session key for every member. The group controller identifies a sponsor, say member M8. The member generates a random number and adds it to its set of existing keys to update them. It then encrypts this random number with its own public key, G to the KM8, and sends it to the group controller. The group controller now uses proxy transformation to convert this into minimum set of messages needed to send R, the random number R, out to all the other members. In this case, it will be order log n messages. So to send a message to members 1, 2, and 3, you can use the proxy key K123. To send it to 4, 5, 6, use this key, and send it to member 7, use its private key. The members now decrypt R and add it to their own set of private keys. Now all the members compute the hash of the new root private key, and that's the new session key. The group controller also adds a random number to its set of private keys, and the alt set of keys are updated. A new session key has been established, and member 9 has been excluded. So I won't go into details of the join protocol. It's a lot simpler because, like LKH, you can use the current session key to send the random value R. Members can decrypt this value with their existing session key, and the sponsor sends a set of keys to the joining user who obviously does not have any keys to begin with. And furthermore, the joining member also contributes a share to its private key, and the system is updated. We've done a complexity analysis of these two schemes, and it turns out that our scheme is as scalable as LKH. We have an additional communication round. This is needed for sending the messages to the joining user. And we have some exponentiation that do not exist in LKH because LKH is symmetric key-based scheme, while ours is public key-based scheme. However, the exponentiations are either a constant number or exponential. We are currently implementing a prototype of the system, and We've got about 9,000 or so lines of code written and partially tested. Initial results are promising, but we haven't completed this testing. So looking at this, we've also identified a couple of challenges for proxy encryption, and we're working to address them. First is the need to generate a proxy key without a trusted third party. So if you remember in the initial example we gave, we had a proxy key, which is the difference between the decryption keys of you, Alice, and Bob. How is that difference generated? If you have a trusted server that's computing the difference, then that trusted server becomes a point of liability. So you need a way to do it in a distributed manner. So Athanasis et al. At Johns Hopkins has developed a solution that addresses this with a novel identity-based encryption scheme. That's done in the context of delegation rights, so it needs a notion of a resource owner, which is not applicable to all scenarios. For example, in group communication, there is no resource owner. Furthermore, it also requires the users to manage 2 private keys instead of 1, so that's a higher overhead. What we have done is to solve this problem using distributed key generation process by sending an additional round of messages with this random number addition and subtraction. My intuition is there is a better scheme out there than both of these to address this challenge. The second problem is resilience to collusion. As I mentioned in our scheme, both in the cells as well as in the group key management scheme, if you add the proxy values and a member's value, you get the group key. And that can be used by the adversary to violate the confidentiality of the system. So this is actually a consequence of using proxy encryption. So you could view it as a limitation of proxy encryption or a challenge to be addressed. And we're exploring solutions that address this problem. We have some initial results, but we still have to work on this a little more. So in conclusion, we show that confidentiality is needed to secure messaging infrastructures. Solutions today either provide no support for this or use trusted servers. Consequently, those servers bear significant trust liabilities. We propose the use of proxy encryption techniques to solve this problem and produce novel solutions that minimize the trust liabilities in servers supporting confidentiality. We've looked at 3 infrastructures, so let's spend a couple of minutes to see what are the different properties of these systems. So first beginning with email. So in an email system, the latencies are very reasonable. If people are okay to wait a second or even a few minutes before the emails are delivered. The group membership is known because once you have a set of valid list subscribers, you know the group. And the proxy encryption that we need has to be done on a per message basis. The solution that we have is very low, which requires that on subscribing, the users get a PGP key pair for doing the encryption and decryption, and everything else works smoothly. Furthermore, even when group members join or leave the group, no other users are affected. That is, this does not suffer from the one effect end problem. In group communication, the latency requirements are much tighter. You want all messages delivered in milliseconds. The group membership is still known, but because of latencies, you do the proxy encryption at key distribution. You cannot afford to do it on a per message basis. Now we don't know the cost because we're still implementing a prototype. We expect the cost to be somewhere between low and medium for the system. By medium cost, I mean that since these are public key messages, the size of the message that is sent over the network will be significantly higher than LKH. So, or the order of kilobytes as opposed to hundreds of bytes. And that takes time and that takes energy. So for low power devices, that may not be a viable solution. To address this, we're looking at extending our protocol to work with elliptic curve cryptography that would reduce the key sizes. In public subscribe systems, the latencies vary depending on applications. Some are okay with milliseconds, some are fine with seconds. But the group membership is not known. Only after the result of the matching and routing algorithms come out do you know the membership of the group that will receive the specific event. And the proxy encryption, therefore, must be done on a per message basis. And the solution costs right now are pretty high because we have this threshold cryptographic service that needs to be maintained. However, new techniques and implementations are showing the threshold cryptographic cost may not be that high. Because in general, if you want to manage infrastructure, such as in stock code dissemination, where you're charging customers for something, the cost is not going to be of the hardware, it is about the administrators who manage the system. It's the human costs that are much higher. But still, I think that there's a lot of scope to find solutions that minimize these costs. With that, we have a few more minutes for questions, and papers are available at this site, or you can send me an email at any time.
When you run the experiment for the scalability, how you set up the system?
I'm sorry?
When you run the experiment for the scalability, the result, how you set up the system?
So we did not set up the entire threshold service. What we did was we looked at all the operations needed in threshold cryptographic, and we used a system that was developed by Mike Marsh at the University of Maryland called Codex. So they have a threshold cryptographic library that they use, and we found out exactly what operations are needed. And then we timed those operations out of context on today's desktop and server machines to time them. So this is a conservative estimate of the scalability, but we have not set up an actual implementation of the threshold system to do so. And we also included networking costs in that. For a gigabit LAN message, the size of the maximum message that is necessary in that system within the proxy service turns out to be 0.35 milliseconds, and those costs were included in that analysis. So we included all the computation and communication costs and then did the conservative scalability analysis estimate.
Any other questions? Let's thank the speaker.
Thank you. Yeah.
Christina said you're going back to the Union Hotel.
Yeah. So yeah, I'll